Greetings of the day to all of you. Well, today I am going to deliver a lecture on Introduction to DC Drives. Up to lecture number 9, it was a general sort of introduction, detailed introduction to electric drives and dynamics of electric drives, torque speed characteristics of loads, torque speed characteristics of different types of motors. DC motors, we have, of course, considered DC shunt motor, separately excited DC motor, DC series motor, and how to find the operating point, how to find the steady state stability of the operating point. And then we have also studied various methods of speed control of separately excited DC motor and DC series motor briefly. Now we are going to study about the complete DC drives, DC motor drives, whereby we will have a DC source or an AC source which is rectified into DC, which is converted into DC. And then we will have a DC motor, and then that DC motor will be driving a mechanical load. And we will study these DC drives, their characteristics, their operation, mathematical analysis, and we will also study them in closed loop operation. So today's lecture is a brief lecture. It is an introduction to DC motor drives. I will write here introduction to DC motor drives. Well, today is, let me write the date. Today is 18th January 2023 and it is Tuesday. Tuesday or Wednesday. It's Wednesday. And we are discussing lecture number 10. This lecture number 10 is about introduction to DC motor drives. Well, when we talk of DC motor drives, obviously the prime mode used is DC motor. It may be either DC series motor or it may be a separately excited DC motor, or it may be DC compound motor, depending upon the application for which we are using the DC drive. Now, these DC motor drives find widespread applications. Till recently, they were very widely used. Their applications, main applications are like in steel rolling mills. I will write here steel rolling mills, textile mills, and then printing presses, printing press, machine tools, etc. Machine tools, vehicles. In highway vehicles also we use DC motor drives, like the windshield wiper, the windshield wipers and the windows, they are controlled by DC motors, because in a vehicle we have a battery which gives DC source, and then a small DC motor is used for controlling the windshields and windshield wiper. So these are some of the applications of DC motor drives. Now, how to control a DC motor drive? The simplest type of DC motor drive will be by using AC to DC converter. Now, we have studied, I'm sure, in your basic power electronics course at your BTech level, you must have studied about various types of these converters, AC to DC converters, whether they are rectifiers or phase controlled converters, single phase rectifiers, three phase rectifiers, single phase controlled converters, three phase controlled rectifiers or phase controlled converters, dual converters, and all that. So I don't need to repeat their operation again here. But in power electronics course, when we teach about these converters, AC to DC converters, we generally analyze them for either a purely resistive load or RL load, or in some cases we also analyze them for RLE load. Now, our DC motor load can be modeled as an active load like RLE load, a load which has resistance, that's the armature winding resistance or armature circuit resistance, then armature circuit inductance, that is R and L, and back EMF of the motor can be modeled by E. So a DC motor can be modeled as an active load, that means an RLE load. I'm sure you must have analyzed some phase controlled converters in your BTech power electronics course for RLE load also, which is an active load. So RLE load basically represents the model of a DC motor load. Anyway, the simplest type of DC motor drive is like if you use uh, this type of arrangement, you have an AC source, then you have a half wave controlled rectifier or half wave converter. This is thyristor T, and this is your DC motor. This is the DC motor. It may be a separately excited DC motor, and field winding is separately excited. This is the field current. This is armature voltage VA. This is armature current IA. You may put a freewheeling diode also across the load. This is the freewheeling diode. This is the simplest type of converter. It is in fact single phase half wave converter. Single phase half wave converter fed DC motor. This is also called single pulse or one pulse converter because we will get for one cycle of AC, we'll get only one half of the DC. It is a half wave converter. It will rectify only positive half cycle of source voltage. That means if this is the source voltage, the load voltage may be something like this. Okay, only during the positive half cycle you will get output voltage across the load. During this positive half cycle, during next positive half cycle, and so on. And of course, there will be some delay angle or firing angle for control of armature voltage and hence speed control. So this is the single, why it is called single pulse converter, because for one cycle of AC you are getting only one pulse of DC output voltage. That's why it's called one pulse or single pulse converter. This is the simplest type of converter that you can use for the speed control or torque control of a separately excited DC motor, or for that purpose for DC series motor also. The advantage of this type of converter is that there is only one device which is carrying current at a time. For example, when during the positive half cycle this thyristor T is fired at certain delay angle alpha, it goes into conduction and current flows like this. Your load gets directly connected across the source and it receives the remaining segment of positive half cycle of source voltage, and armature current flows in this direction. Since only one device is conducting the armature current, the voltage drop across this device may be say 1 to 2 volts or about 3 volts. So voltage drop is very small. So therefore, since the voltage drop is very small, this type of converter is suitable for controlling DC motor drives of very low voltage rating and very low power rating. Because when the voltage rating of the drive is very small, say for example you may have a 12 volt or 24 volt DC motor, okay, and you want to control, and then if the thyristor is dropping 2 to 3 volts, you may not get required voltage across the DC motor drive, across the DC motor. So therefore, instead of using two thyristors which are dropping the voltage, okay, you use only half wave converter in which only one device drops the voltage 2 to 3 volts. So therefore, this type of converter finds its application for driving low power and low voltage DC motor drives. However, this suffers from some serious drawbacks. I mean, you may feed this converter through a step down transformer like this. This is a step down transformer because the input voltage may be 230 volts, 50 hertz AC, but the drive may be operating at say only 12 volts. So you have to step down the voltage and then using the delay angle control for controlling the output voltage for speed control or for adjusting the output voltage at the desired level. So the main drawback of this type of converter, half wave converter, is that it results in the flow of DC. There will be a strong DC component of current flowing in the transformer secondary as well as transformer primary. That will result in deep saturation of the transformer core and higher losses in the transformer. Okay. Another drawback is that since you are rectifying only the positive half cycles, the average output voltage the average output voltage obtained is less. So the main drawback is that transformer carries a very rich DC component of the current. So that's why this type of converter is generally not used. It is used in exceptional cases, say for toy motors or for very, very small low power and low voltage rating motors. Otherwise, this type of converter does not find its application. Another type of converter is two pulse converter. Now let us study about single phase two pulse converters feeding a DC motor drive. So among the two pulse converters, you may have this type of converter. This is armature circuit resistance, say RA. This is armature circuit inductance LA. And this is the back EMF of the motor, EB. The output voltage of the converter or armature input voltage, motor input voltage is VA and motor current is IA. This is again, the converter may be fed through a step down transformer. It may be fed through a transformer. This is the transformer. This is the source voltage and this is load voltage. These are the thyristors T1, T2, T3 and T4. And the field winding is a separately excited DC motor. The field voltage is VF and field current is IF. We can very clearly see, now the question is, how do we get this field voltage and field current? Again, from the same transformer, you may take two connections and you may have a single phase single phase bridge rectifier. This is a single phase bridge rectifier. The input to this rectifier is this transformer output AC voltage, and what this rectifier does, it converts this AC voltage into DC voltage, and this is the field voltage VF, and it is fed to the field winding. So field winding is fed by a bridge rectifier, uncontrolled rectifier, if you need constant field current. But if you want to change the field flux also, then this bridge rectifier may be replaced by phase controlled converter, just like armature converter is a phase controlled converter. Anyway, in most of the cases, if you need speeds below base speed, you need to control only armature voltage, keeping the field flux or field current constant. In that case, this may be a bridge rectifier, diode bridge rectifier, uncontrolled rectifier. So it converts AC into DC, and this DC field voltage VF is fed, and it results in the flow of field current IF. Now this field voltage should be equal to the rated voltage of the field winding, so that rated field current IF flows. So accordingly, you have to choose the turns ratio of the transformer, step down transformer. If this transformer does not meet those requirements, it does not produce the rated current and rated field voltage, then you may use another transformer, a different transformer like this. You may disconnect it from here and you may use a different transformer like this, in which the turns ratio is chosen in such a way that when the rectifier rectifies this AC voltage, it converts it into rated DC voltage, rated field voltage, which results in flow of rated current IF. Anyway, this is how a DC motor drive, separately excited DC motor drive, is fed by two pulse converter. This two pulse converter, what type of converter is this? All the four devices are thyristors. All of you, I am sure, know this is a single phase fully controlled converter. I will write here single phase fully controlled converter. This is called single phase fully controlled converter, or this is also called single phase full converter. In short, we call it full converter. So by delay angle control, firing angle control, you are able to control the average output voltage. This average output voltage of the converter, which is same as armature voltage, it is controllable. It is controllable from 0 to rated value. This armature voltage is controllable from 0 to rated value by delay angle control. You may control delay angle from 0 to 180 degrees or 0 to 90 degrees. Okay. So you get a wide range of armature voltage control, and you get a wide range of torque control or speed control of the motor. Okay. Before the advent of power electronics technology, it was very difficult to control this DC voltage, armature voltage. Ward-Leonard method of speed control was used, which was a very costly, very bulky method and very inefficient method. Now a simple single-phase full converter can do the same job. It can do the job very efficiently. It's a static converter. It does not have any rotating parts. By delay angle control or by firing angle control, alpha, variable output voltage or variable armature voltage can be produced, and a wide range of speed control can be achieved. Okay, so this is single phase full converter. Similarly, you may have three phase full converter. I mean, if you go for three pulse converters, of course, full converters, fully controlled converters or full converters. The three pulse converters are like this. It's not three pulse, I'm sorry, it is six pulse converters. If you go for six pulse converter, you have three pulse converters also, but three pulse converters are generally not used. For high power applications, we go for six pulse converters. Six pulse converter is basically a three phase fully controlled converter, as you can see, or three phase full converter. It's a three phase full converter which converts AC into controlled output, controlled DC output. Three phase AC is converted into controlled output DC, variable DC output. This is three phase AC, and this is the DC, say armature voltage VA plus minus. So this is armature circuit resistance RA, armature circuit inductance LA, and this is the back EMF of the motor plus minus EB. Armature current is IA, and this is a separately excited DC motor. So again, you may use a three-phase bridge rectifier, which will convert AC into DC and produce DC field voltage VF, resulting in the flow of field current IF, which is equal to the rated field current. And by firing angle control, alpha control, you can achieve a wide range of torque control, speed control, because this VA changes when alpha changes. You produce a controllable armature voltage, a variable armature voltage, and hence a wide range of speed control can be achieved. Why is it called a six pulse converter? Because for one cycle of AC, let's take phase A. This is phase A, phase B, phase C. If you take phase A, one cycle of AC. For one cycle of AC of phase A voltage, you get at the output six pulses of DC. Say for example, this is phase A voltage, VA. Say phase voltage VA. Output voltage will be having six pulses. 1, 2, 3, 4, 5, 6, depending upon the delay angle. Delay angle can be anything. Okay. So this is the output voltage VD or VA, armature voltage, output voltage. So for one cycle of phase voltage VA, we get six pulses of DC voltage. That's why it's called six pulse converter. Higher the number of pulses, better is the performance. There is less and less ripple in the output voltage. Lesser the ripple in the output voltage, lesser will be the ripple in the armature current, and less the ripple in the armature current, less will be the ripple in the armature torque, and more smoother will be the operation of the motor. Just like we have six pulse converters, we can have 12 pulse converters also. How do we produce a 12 pulse converter? A 12 pulse converter is produced like, it comprises of two 6 pulse converters connected in series like this. Let me show you the power circuit diagram of a 12 pulse converter feeding a DC motor drive, a separately excited DC motor. It is like this, one 6 pulse converter, and then another 6 pulse converter is here just below it. This 6 pulse converter, we have a primary winding. Let's suppose we have a star connected primary winding. This is three phase AC, and secondary winding may be this secondary winding may be star connected. It will have two secondary windings. This star connected secondary winding will feed converter 1. Let's call this converter C1 and this as converter C2. It is feeding converter C1 like this. And then we have another secondary winding which is not star connected, which is delta connected. For example, like this. It's a delta connected secondary winding. It is feeding second converter number 2 like this. Okay. So we have a transformer with one primary and two secondaries. The primary winding may be Y connected or star connected, and it has two secondaries. One is Y connected, another is delta connected. This Y connected secondary transformer winding feeds converter C1, which is a 6-pulse converter, and this delta connected secondary winding feeds another 6-pulse converter C2, and output is available across these terminals. This is the positive bus, this is the negative bus, and you connect the motor between positive and negative bus like this. This is your DC motor. So this is back EMF EB, armature circuit resistance is RA, armature circuit inductance is LA, and this is your output voltage of 6-pulse converter or armature voltage. You can call it armature voltage, and this is armature current or load current IA, and this may again be a separately excited DC motor BF and IF. This is field current IF. So this is a 3-phase 12-pulse converter. Why is it called 12-pulse converter? Because for one cycle of AC, let me take one cycle of AC. Briefly, I will show you here. For one cycle of AC of any voltage, any phase voltage, A, B, or C, at the output you get 12 pulses of DC voltage. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So you get 12 pulses of output voltage. So you can see the ripple content in the output voltage, armature voltage, is very, very small. So therefore armature current IA will be almost constant armature current like this. It will be ripple free current, and it will result in smooth torque development, because torque development is directly proportional to armature current. And if armature current is ripple free, the torque will also be pulsation free or ripple free, and it will result in smooth operation of the motor. So this is about how you can have 24 pulse converters also, 48 pulse converters also, but the arrangement is very complicated. The cost of those converters is also very high. So this is 12 pulse converter. Usually we go up to 6 pulse converters. Okay. Now this is about full converter. And what about half controlled converter? I will take single phase half controlled converter now. Half controlled converter. Single phase half controlled converter or single phase semi converter. It's also called semi converter. And of course, these semi converters are 2-pulse converters. I'm going back to single phase version of the converter, and it is feeding a DC motor drive. It looks like this. See, it comprises of 2 thyristors and 2 power diodes. The lower 2 thyristors are replaced by diodes, power diodes. So this is thyristor T1, thyristor T2, this is power diode D1, and this is power diode D2. And this may be a single phase AC through transformer, step down transformer, of course. This is our DC. This is the transformer secondary winding, AC step down voltage, and this is the motor, armature. This is armature circuit resistance RA, inductance LA, back EMF EB. Field winding may be separately excited with field current IF, and armature voltage or output voltage is VA, which is controllable, plus minus, and armature current or load current is IA. So this is single phase half controlled converter or single phase semi converter, where we have 2 thyristors and 2 power diodes. This here also you can go for alpha control, firing angle or delay angle control, and you can get very wide range of output voltages. You can vary output voltage from 0 to maximum value. So 0 average output voltage you can vary from 0 to max. Say for example, if alpha is 0 degree, 180 degrees, output voltage is 0, And as you decrease alpha, average output voltage increases till alpha reaches 0 degree. At alpha equal to 0 degree, output voltage is maximum. So therefore you vary the delay angle or firing angle from 0 to 180 degrees, and you get average output voltage from 0 to VA max. Okay, and remember, this maximum voltage that you get corresponding to alpha equal to 0 degree should be equal to the rated voltage of the motor. When you choose a motor, the motor is rated for certain voltage. Say for example, the motor may be rated for 240 volts DC. So therefore, when alpha is 0, how much armature average output voltage should be produced? Average output voltage should be equal to VA max, and it should be 240 volts. And then as you increase alpha, average output voltage will go down and you will get speed control. You'll get a wide range of torque control and speed control. So remember, when you choose a step down transformer here, you have to choose the step down transformer in such a way that for alpha equal to 0, that's the minimum delay angle, you get the maximum armature voltage, and that maximum armature voltage VA max should be equal to the rated voltage of the motor. Say for example, the rated armature voltage or rated motor voltage may be 240 volts. Okay, you use this transformer, step down transformer, in case AC voltage for alpha equal to 0 degree gives an output voltage which is more than rated voltage, say more than 240 volts. Okay, that's why you use a step down transformer here, so that for alpha equal to 0 degree you get rated motor voltage VA max, which is equal to, say for example, 240 volts. If on the other hand your AC supply has an RMS value such that for alpha equal to 0 degree you get maximum armature voltage which is equal to rated motor voltage, then in that case you don't need this transformer. Okay, so that's why you need this. This explains why we need a transformer. In a similar way, we can have three-phase half-controlled converter, three-phase half-controlled converter, or three-phase semi-converter. Remember, this three-phase half-controlled converter or semi-converter is not a 6-pulse converter, it's a 3-pulse converter. Before this, just few moments back, we have studied about three-phase full converter or three-phase fully controlled converter. That is a 6-pulse converter. But three-phase half-controlled converter or three-phase semi-converter is a 3-pulse converter. So it is like this. We have 3 thyristors in the upper group, positive group of devices, and negative group or lower group of devices are not thyristors, they are power diodes. This is three-phase AC supply. It may be given directly or through step-down transformer. So this is three-phase AC, and this is the output. This is where you connect the motor. Across the DC bus, you connect the motor. This is back EMF of the motor. This armature resistance RA, armature inductance LA. This is the field winding with field current IF, which is equal to rated current. The load voltage or armature voltage is VA, which is controllable, plus minus, and armature current or load current is IA. So again, alpha control is done here by alpha control, delay angle control or firing angle control. A variable or controllable armature voltage is achieved, and hence a wide range of torque control and wide range of speed control is achieved. Okay, this is about three-phase half-controlled converter. Now the question, and then we have three-phase dual converter. I will come to that later on. The question is when to use a full converter, whether it is single-phase full converter or three-phase full converter, and when to use converter, semi-converter, single-phase semi-converter or three-phase semi-converter. When to use it? So for example, you have let us take a single-phase full converter again. This is a single-phase fully controlled converter or single-phase full converter which is feeding a load. This is our DC separately excited motor which acts as a load. This is the back EMF of the motor. This is the armature voltage or load voltage VA, plus minus, and load current or armature current is IA. And this is the separately excited field winding. Field current is equal to rated current IF. and field voltage is Vf, which is obtained through a bridge rectifier. This is our single phase AC. Single phase AC. Okay. And these are the thyristors T1, T2, T3, T4. By alpha control, a variable or controllable armature voltage is obtained, and hence we get a wide range of speed control. Symbolically, it is shown like this. Let me show you the symbolic representation of full converter. It is symbolically shown like this. Symbolically, we show one thyristor within this box. It means it is a full converter or fully controlled converter comprising of 4 thyristors like this. Okay, now this is armature voltage or load voltage VA plus minus, and armature current or load current is IA. Armature circuit resistance is RA, armature circuit inductance is LA, and back EMF of the motor is EB. And this is the field winding with field current IF, right? So this is a single phase full converter. A 3-phase full converter is symbolically shown like this. Instead of one line, we show there 3 lines, that's all. And how many thyristors will be there? In a 3-phase full converter, we don't have 2 legs, we have 3 legs. So we have 1, 2, 3, 4, 6 thyristors. In a single phase full converter, it's a bridge converter, we have 4 thyristors. But in a 3-phase full converter, we have 6 converters. Sorry, 6 thyristors. Okay, symbolically it is shown like this. Single phase full converter is symbolically shown like this, and 3-phase full converter is symbolically shown like this. And then again we may have a DC motor as a load, and this is it. This is how we symbolically show it. Now let me again draw symbolic representation of a single phase full converter. So this is single phase AC. Now this is armature circuit resistance RA, armature circuit inductance LA, and this is the back EMF of the motor plus minus EB. This is the field current IF, which is equal to rated field current. The load voltage or the armature voltage is VA. It has average value VA, and average load current or armature current is IA. Now we know that the output voltage, I'm sure you have studied in your basic power electronics course, the average output voltage of a single phase fully controlled converter, VA, which is equal to our average armature voltage in this case. It is given by this relation 2 root 2 Vm, or it is given by 2 Vm by pi cos alpha. I'm sure you know about this relationship. Or VA is equal to, Vm is the peak of the input voltage. The input voltage is Vs equal to Vm sine omega t, where Vm is the peak of the input voltage, and it is equal to root 2 Vs sine omega t, where Vs is the RMS value of input voltage. So in terms of peak input voltage, the average output voltage or average armature voltage, VA, capital VA, is equal to 2 Vm by pi cos alpha. And in terms of RMS value, it is 2 root 2 Vs by pi cos alpha. 2 root 2 divided by pi is equal to 0.9, so it is 0.9 Vs cos alpha. Now alpha is variable. Since alpha is variable, the average output voltage also is variable. Now what is the range of alpha? Alpha has 2 ranges, 0 to 90 degrees. When you control alpha from 0 to 90 degrees, say for alpha equal to 0 degrees, what is the average output voltage? VA. VA is cos 0 is 1, so VA is 0.9 Vs, or it is equal to 2 root 2 by pi Vs. It is equal to 0.9 Vs, and it is the maximum voltage that you will get. Vs is the RMS value of input voltage. This is the maximum voltage that you will get for alpha equal to 0 degree across the motor armature terminals. And when you select a motor, you already know what is the rated armature voltage of the motor. And for alpha equal to 0 degree, your converter should produce the rated voltage of the motor. So this is equal to rated voltage of the motor, Va max. Then as you increase alpha above 0 degree, cos alpha decreases. As alpha increases, cos alpha decreases, and average output voltage decreases till at alpha equal to 90 degrees. What happens? At alpha equal to 90 degrees, cos 90 degrees is 0. So average output voltage is 0. So therefore, when you vary the delay angle or firing angle from 0 degree to 90 degrees, you get average output voltage which is equal to Va max up to 0. Va max less than or equal to Va less than or equal to 0 degree. That means for alpha equal to 0 degree, average output voltage is maximum Va max, which is given by 0.9 Vs. We have already seen that here. And then as alpha increases, average output voltage decreases till at alpha equal to 90 degree, cos 90 is 0, average output voltage is 0. Okay. So therefore you can get output voltage from 0 to maximum when you control the delay angle or firing angle from 0 to 90 degrees or 90 to 0 degrees. And average output voltage will be always positive. Okay. So therefore, if you see in the quadrant operation, say for example, this is positive armature current, IA. This is negative armature current minus IA. This is positive average output voltage VA. This is negative average output voltage minus VA. So for delay angle varying from 0 to 90 degrees, you get average output voltage varying from 0 to Va max, but it is always positive, so you get positive average output voltage. Okay, so your DC motor drive operates in first quadrant of voltage and current. And in the first quadrant, what is power, armature power or motor power? It is average output voltage into average output current, average armature voltage into average armature current. Since average armature voltage is positive, current is also positive. So this is positive. Positive power means that your machine is operating as a motor. As a motor, it is drawing power from the source, electrical power from the source at any value of alpha from 0 to 90 degrees, converting that electrical power into mechanical power and drives the motor and its driven load. That mechanical power or mechanical energy is absorbed by the mechanical load. So mechanical power drives the load. Okay, so this is forward motoring mode. In terms of torque speed characteristics, we have already studied about torque speed characteristics. This is positive torque developed by the motor, negative torque, positive speed of the motor, and this is the negative speed of the motor, and it is operating in first quadrant. In torque speed characteristic also it is operating in the first quadrant, because in first quadrant, say let us suppose this is the machine is developing torque in this direction and it's making the motor run in the same direction. The motor and its driven load runs in the same direction, say clockwise direction. So power is equal to omega into T, omega m to T. Since omega m is positive, this clockwise direction is taken as positive. Torque is also positive. So power is positive. So from torque speed characteristic also, power is positive. From VAIA characteristic also, we find that PA, the power drawn by motor from the source, is positive. That means the machine is acting as a motor. It is drawing electrical power from the source, converting that electrical power into mechanical power, and that mechanical power is used to drive the motor and its load. Okay. Now what about if you change delay angle from 90 to 180 degrees? For 90 to 180 degrees, if alpha is changing from 90 to 180 degrees, alpha greater than 90 degrees but less than or equal to 180 degrees, the average output voltage will vary from 0 to minus Va max. At alpha equal to 90 degrees, because we know average output voltage, I will write here again, it is given by 2 root 2 Vs by pi cos alpha. For alpha equal to 90 degrees, average output voltage is 0. For alpha greater than 90 degrees, cos alpha becomes negative, so average output voltage becomes negative till at alpha equal to 180 degrees. Cos 180 degrees is equal to minus 1. So average output voltage will be minus 2 root 2 Vs by pi, and we call it minus VA max. This is the maximum average output voltage developed by the converter. So converter develops maximum average output voltage, but that is not positive, that is negative. Okay. So therefore, for alpha greater than 90 degrees, this mathematical equation tells us that for alpha greater than 90 degrees, alpha greater than 90 degrees, up to 180 degrees, the average output voltage becomes negative till at alpha equal to 180 degrees, it becomes maximum negative, VA max. And in this talks, this characteristic, four quadrant characteristic, VA versus IA characteristic, what is the negative voltage? Current will still remain positive, but average output voltage will become negative. What is the negative average output voltage? This axis is the negative voltage. So therefore, our converter, our DC motor drive will operate in the fourth quadrant. This is first quadrant, this is second quadrant, this is third quadrant, and this is fourth quadrant. In the fourth quadrant, you can very clearly see current is positive, but average output voltage has become negative, because for alpha greater than 90 degrees, average output voltage becomes negative. Okay, and what is power drawn by machine from the source? That is average output voltage. What is that? That is not positive now, that is negative, minus VA into current. Current is always positive. See, current cannot be negative. Negative current means current flowing in this direction. Current cannot flow in the opposite direction, because the converter comprises of thyristors, and thyristors always conduct from anode to cathode, not cathode to anode. So current reversal is not possible. However, average voltage polarity reversal is positive. See, if it was plus minus, now it can become plus minus like this. This can become plus, this can become minus. Average output voltage can become negative. Now, since VA is negative here, IA is positive, what is average output? What is the power? It is negative. And what does negative power say? Negative power says that the machine is not operating as a motor, it is operating as a generator. It is converting the inertia or kinetic energy of its rotating parts into electrical energy. In other words, it is taking the mechanical energy of rotating parts, converting that into electrical energy, and supplying that electrical energy back to the source. So isn't it the regeneration mode? Yes, it's the regeneration mode. And in the regeneration mode, the if the speed of motor was previously in this direction, what is torque? Power is becoming negative. Okay, negative power means the motor is operating as a generator. As a motor, it was developing torque in this direction, but as a generator, the direction of torque reverses. So torque will be in this direction. So you can see torque opposes the motion. Motion is in the clockwise direction, but torque is developed in the anti-clockwise direction. So this torque acts as a braking torque, and it tries to slow down the motor. Okay, so torque is negative, and in this torque speed characteristic, what is the negative torque? Negative torque is along this axis, minus x-axis. So therefore, our drive operates in second quadrant. On VI, this characteristic, the drive either operates in first quadrant or in fourth quadrant. But on torque speed characteristic, it operates in the first quadrant and second quadrant. Because in first quadrant, speed is positive, speed is greater than 0, torque is also greater than 0, power is positive. In the second quadrant, speed is positive, but torque is negative. Since power is equal to speed into torque, power will be less than 0, negative. Why? Because torque is negative. So negative torque means, negative power means the machine is not operating as a motor, it is operating as a generator, and it is operating in the forward regeneration mode. So if this is forward motoring mode, this will be forward regeneration mode. So this is what happens in a DC drive. So in a DC drive, you can operate the motor either in forward motoring mode or in forward regeneration mode. But see, we know that armature current IA is given by V minus VA minus EB by RA. In the previous lecture, I have explained to you that regeneration will occur only when back EMF is greater than VA. When VA is greater than back EMF, current is positive and it is forward motoring mode. But when EB is greater than VA, current will be negative, and negative current means the torque is negative, and negative torque means forward regeneration mode. But the problem here is that even if you make EB greater than VA, current cannot reverse its direction. You see, current cannot reverse its direction. Can it reverse its direction? When EB is greater than VA, IA is negative. Negative current means current will reverse its direction. It cannot reverse its direction because the converter does not allow reverse flow of the current. So therefore, what you have to do in order to operate your drive in the second quadrant, in the forward regeneration mode, you have to reverse the polarity of the back EMF. And you have to operate your converter at alpha greater than 90 degrees, because just few moments back we know the average output voltage is given by 2 root 2 Vs by pi cos alpha. For alpha greater than 90 degrees only, then we say that our converter is operating in the fourth quadrant, or our drive is operating in the second quadrant, that is the forward regeneration mode. For alpha greater than 90 degrees, just few moments back we have seen that average output voltage is negative. So therefore, what will be average output voltage? It will be negative. Negative means this is plus, this is minus for alpha greater than 90 degrees. So when this is plus and this is minus, what we will do to back EMF? We will try to reverse the back EMF polarity also. Plus, minus. Now the question is, how can we reverse the back EMF polarity? There are two ways of doing it. Either you reverse the armature terminals. I mean, ये अगर A है और ये AA है. In the motoring mode, A was connected here and AA was connected here. In the regeneration mode, what you have to do? A you have to take here and AA you have to keep here. I mean, what you have flipped the connections. It is like this. This is your armature. Okay. So what you have to do? Converter. This is A. This is AA. This is plus minus. So this converter. This is the output of converter. The connections are flipped like this. This is connected here and this is connected here. This is the output of converter. So we have flipped the armature terminals. So therefore this is plus, this is minus. We have connected it here and we have connected it here. We have connected this to minus. We see we have connected it to minus, and we have connected negative bus to positive. Negative bus, this is negative bus. This is connected to, this is connected here. This is positive bus is connected here. Okay, this is positive bus, this is negative bus. Positive bus is connected to A, positive bus is connected to A, and negative bus is connected to A. Negative bus is connected to A. So therefore, if you flip the armature terminals, you interchange the armature terminals, the back EMF polarity will reverse like this. Another way is that instead of flipping the armature terminals, you interchange the field terminals. I mean field current reverse कर लीजिए. Normally field current is flowing in this direction, make it flow in the opposite direction by reversing the connections like this. When you do that, in that case also, since the field current has reversed its direction, flux will also reverse and back EMF will reverse its polarity. Now regeneration can very easily take place. What happens? Now this is minus plus. ये देखिए ये आपका back EMF है. It's a source basically. और ये आपका converter average output voltage है. This is converter average output voltage, VA. They are connected like this. Negative bus is connected to negative, positive bus is connected to positive. Now they apply this equation. This equation tells you that in order that regeneration should take place, back EMF should be greater than VA. The back EMF of the motor should be greater than average output voltage, or greater than armature voltage. When EB is greater than VA, IA will become negative. IA will be. This is EB, this is VA. So how do you obtain this VA negative? See, you have made EB negative either by interchanging or flipping the armature terminals or by flipping the field terminals. Okay, that we have done. But EB will have a fixed magnitude. How can we then make EB greater than VA? VA is controllable. VA is alpha controlled. Here you make alpha greater than 90 degrees and average output voltage has reversed its polarity. For alpha greater than 90 degrees, average output voltage becomes negative like this. And then by controlling alpha, you can adjust the value of VA such that VA is less than EB, or in other words, EB is greater than VA. So EB by alpha control here, of course, alpha is greater than 90 degrees, no doubt about that. But how much You have to adjust the value of alpha. Your controller will adjust the value of alpha greater than 90 degrees in such a way that VA is less than EB, or in other words, EB is greater than VA, and then current flows like this. Current does not, in motoring mode, current flows from source to, EB, source to EB. But in regeneration mode, current should come out of this EB and it should flow into the source. Say मोटरिंग मोड में करंट यहाँ से निकलती है और यहाँ जाती है, बट रिजनरेशन मोड में करंट यहाँ से निकलेगी और सोर्स में जाएगी. सो ईबी करंट कम्स आउट ऑफ ईबी एंड इट इज फ्लोइंग इन दिस डायरेक्शन. अगर देखा जाए from the point of view of converter, from the point of view of converter, current has same direction, but from the point of view of polarity of EB and polarity of average output voltage or armature voltage, current has reversed its direction. It is not flowing from VA to EB. In motoring mode, it was flowing from VA to EB, but in regeneration mode, it is flowing from EB to VA. You can very clearly see. So therefore, when it is flowing like this, what you have done, from the converter point of view, armature current has not changed its direction. It is in the same direction. But it is not flowing from VA to EB, it is flowing from EB to VA. So that's where regeneration occurs. Okay? So average output voltage becomes negative. So current is still positive. So our converter is operating in the fourth quadrant. And from torque speed point of view, since current has reversed its direction, it's not flowing from VA to EB, it's flowing from EB to VA. Current has become negative, so torque has also become negative, and negative torque you plot along this axis. So speed is still positive, okay, motor is still rotating in this direction, but torque has become now negative. It's acting as a braking torque, and you can slow down the motor. And let me tell you, you cannot only slow down the motor, you can even stop the motor. How? See, when this braking torque, regenerative braking occurs, torque opposes the motion of the motor. Motor slows down. When motor slows down, EB decreases. Because when motor slows down, omega m decreases. So therefore, EB, which is proportional to omega m, also decreases. And VA may again become greater than EB, but you don't allow VA to become greater than EB. You have to always maintain EB greater than VA. So you have firing angle control here. You increase the delay, you decrease the delay angle from 180 degrees towards 90 degrees. When you adjust the delay angle, you can always maintain EB greater than VA like this. And as long as EB is greater than VA, the regeneration will take place. Motor will further slow down, speed will further come down, EB will decrease, but you decrease simultaneously VA also, so that you maintain EB greater than VA till motor finally comes to standstill, it stops. Okay, so therefore in the forward regeneration mode, using the phase controlled converter, you can slow down the motor and you can also stop the motor. It's not used only for halting or holding the speed, slowing it down. You can use this converter for slowing down the motor and the drive, and also stopping it, bringing it to standstill. Fine. So this is one way of understanding it. Another way of understanding it is like this. You have to understand regeneration. Forward regeneration will take place like this also. Say for example, this is again your phase controlled converter, full converter of course, which is fed from AC, single phase AC, and this is your motor A, AA, and this is back EMF EB. This is armature circuit resistance RA, inductance LA. This is the field current IF, which is constant. This is armature voltage plus minus VA. In the motoring mode, current is flowing like this. Okay. Now let us suppose our drive is not a train, it is not a vehicle, or it is not any other load. It is a hoist. Say for example, what does a hoist do? In the motoring mode, hoist develops a torque. Say your machine is operating in the motoring mode. Alpha is less than 90 degrees. I mean 0 to 90 degrees is alpha. Average output voltage is positive. And according to armature voltage, so the motor runs at certain speed and it lifts the load. Say for example, it lifts the load from ground level to some height. It may be 20th floor of the building. It may be a 30th floor of the building. So load is taken up. When load is taken up, load upar gaya, and it has been the cage has been unloaded. लोड यहाँ से निकाला गया. Now what should happen to the cage? Cage नीचे आनी चाहिए. When cage comes down due to the force of gravity, it will come down very fast. Okay? या अगर केज में आपने सपोज यू हैव टेकन एन एम्प्टी केज अप से अप टू 20th फ्लोर ऑफ द बिल्डिंग, और वहां पे आपको कोई लोड ऊपर से नीचे 20th फ्लोर से नीचे लाना है, ग्राउंड फ्लोर, एंड यू हैव नाउ लोडेड द केज एट द 20th फ्लोर. नाउ केज इज लोडेड और यहाँ से काउंटर वेट है, द लोड ऑफ द केज इज ग्रेटर देन लोड ऑफ काउंटर वेट. ड्यू टू द फोर्स ऑफ ग्रेविटी दिस केज विल कम डाउन वेरी फास्ट, and when it comes down very fast, it overspeeds. When it overspeeds, the motor also overspeeds. And see, when the cage is moving from ground floor to up, motor is say running in this direction, clockwise direction. Torque is also in this direction. Okay, like this. At 20, it was an empty cage. At 20th floor, now we have loaded the cage. Now we have to move it down. When it moves down, when it moves up, it runs in the clockwise, motor runs in the clockwise direction, and when it moves down, the motor runs in the anti-clockwise direction. So motor की speed अब reverse हो गई, negative हो गई speed. Speed has become negative. Here speed is greater than zero. Now when cage moves up and when hoist moves down, speed has become less than zero. Okay, negative speed. Now speed is in this direction. I repeat, when the hoist goes from ground floor to say 20th or 30th floor, torque is developed by motor because it has to take cage up. It's the positive torque. Speed is also positive. This speed is considered as positive speed, which takes the crane up. And at 20th or 30th floor, you have loaded the cage. The cage now comes under the force of gravity. It comes down very quickly down. And since it comes down, the direction of speed reverses. Moving from ground floor to top floor, speed is in clockwise direction, and when it moves from top floor to ground floor, speed reverses, it becomes negative. और जब speed reverse हो जाती है, what happens to the back EMF? Since back EMF is directly proportional to speed, जब speed negative हो जाती है, back EMF भी negative हो जाता है, तो automatically the back EMF of the motor becomes negative. And when back EMF of the motor becomes negative, now you have to operate your converter not as a rectifier, you have to operate it as an inverter. You have to make alpha greater than 90 degrees. जब आप alpha greater than 90 degrees करेंगे, so this VA will reverse its polarity. This will be plus, this will be minus. So we have neither interchanged the armature terminals nor have we interchanged the field winding terminals as we had done in the previous case. Hoist is coming down, speed has reversed. So obviously the back EMF has also reversed. AA has now become positive, A has become negative. So in order to limit the magnitude of current is now coming out from EB and it's flowing of course it's flowing in the same direction. But earlier it was flowing from VA to EB. Now it is coming from EB and flowing towards VA. And you have to limit the magnitude of the current. In order to limit the magnitude of the current, you have to operate your converter in the inversion mode. And we know that converter operates in the inversion mode for alpha greater than 90 degrees. You have to make, in the motoring mode, alpha was less than 90 degrees. In the regeneration mode, now alpha has to be greater than 90 degrees so that the average output voltage becomes negative like this. Now again, it's this type of situation. This is average output voltage and this is back EMF. Back EMF has reversed its polarity due to speed reversal. To limit the magnitude of current, VA should be, EB should be greater than VA. You have to make alpha greater than 90 degrees, but in such a way that average output voltage is less than EB. So EB is slightly greater than VA. It should not be much greater than EA, because if EB is greater than VA by a larger amount, it will result in huge current that may burn the armature winding. So EB has to be greater than VA, but by a small amount, maybe 2 to 3 or 5%. And that is the case, the current flows like this. Okay. अब आप देख सकते हैं current has become negative, it is flowing from EB to VA, or in other words average output voltage you have made negative. Your converter is again operating in the fourth quadrant because average output voltage is negative, and in the fourth quadrant we are operating in the regeneration mode. But the question is, will our drive operate in forward regeneration mode or reverse regeneration mode? In this case, in the previous case, our drive was operating in the second quadrant in the regeneration mode, that was forward regeneration mode. But for this particular case, in case of a crane or a hoist or a lift, when lift comes down or when hoist or crane comes down, speed reverses. तो पॉजिटिव स्पीड ऊपर है, नेगेटिव स्पीड नीचे है, बट टॉर्क रिमेन्स इन द सेम डायरेक्शन, टॉर्क रिमेन्स स्टिल पॉजिटिव. ओके, बिकॉज व्हेन जब स्पीड रिवर्स हो जाती है, ओके, व्हेन स्पीड रिवर्स हो जाती है, ये स्पीड है, टॉर्क is in the opposite direction, because now current is flowing like this. It's flowing from EB to VA. It is a regeneration mode of operation. Our converter is operating in the fourth quadrant where power is negative. That means when hoist comes down, it comes down very quickly. The motor machine reverses its speed and it overspeeds. EB becomes greater than VA. You have to increase alpha, you have to make alpha greater than 90 degrees so that converter operates in fourth quadrant. And your drive now operates in the regeneration mode, such that when the speed reverses, torque is opposite to the direction of motion. Speed is in this direction, torque should be positive. You can see speed has become negative, but torque should remain positive, so that this torque acts as a braking torque and it does not allow crane come down at a dangerously high speed. The crane will come down and it will come down at a steady speed, and simultaneously when the crane is coming down, it converts mechanical energy into electrical energy. That electrical energy is fed back to the source. This is regeneration, but our drive is operating not in second quadrant, it is operating in fourth quadrant. And if you remember, fourth quadrant is reverse regeneration mode, or this is also called reverse braking mode. Okay, so when the crane was moving up, our drive was operating in first quadrant, forward motoring mode. And when crane comes down, our drive is operating in the fourth quadrant, reverse regeneration mode. In the reverse regeneration mode, power is omega into T. Omega has now become negative, so it is minus omega m. Torque is still positive, so power is negative. Negative power means our machine is not operating as a motor, it's operating as a generator. And as a generator, it is converting the mechanical energy of the crane and the motor into electrical energy, supplying that electrical energy back to the source and saving the energy, and simultaneously applying a braking torque and slowing down the crane so that crane comes down slowly at safe speeds. So therefore, in the nutshell, there are two ways by means of which you can perform the uh, regeneration. You can operate the machine in the braking mode. First is you operate in the forward regeneration mode, that second quadrant of torque speed characteristic. That's possible only when the armature terminals or the field terminals are flipped, interchanged, and you operate converter at alpha greater than 90 degrees. In that case, speed will remain positive, but torque will become negative and your drive will operate in forward regeneration mode. Second case is when this type of load is there. Say a crane moving ground floor to top floor and then coming down from top floor to ground floor. When it moves from ground floor to top floor, it's operating in the first quadrant. Your converter is operating at alpha less than 90 degree, first quadrant. Your motor is also operating in the first quadrant as a motor. So it is forward motoring mode. But when the crane comes down, it comes down at a very high speed, and speed reverses. When speed reverses, back EMF reverses. You have to operate your converter for alpha greater than 90 degrees so that the average output voltage reverses its polarity like this. And your converter again operates in the fourth quadrant, but drive does not operate in fourth quadrant now. It operates in, sorry, drive does not operate in second quadrant. It operates in fourth quadrant. It was earlier operating in forward motoring mode. Now it will operate in forward regeneration mode because speed has become negative. Okay, so this is how regeneration takes place in drives. And since average output voltage, I will write it again, is equal to 2 root 2 Vs by pi cos alpha, and our converter operates in first quadrant and fourth quadrant of I versus V characteristic. This is first quadrant, forward motoring mode. This is fourth quadrant. Fourth quadrant, it may be forward regeneration mode or reverse regeneration mode, depending upon what type of application is there. So we can say this is a regeneration mode or braking mode. Okay, if you plot average output voltage or average armature voltage versus alpha, you'll get this type of characteristic. This is alpha and this is average armature voltage or average output voltage plus minus. When alpha is 0, average output voltage is maximum, that is equal to 2 root 2 Vs by pi. So that is zero point 0.9 Vs. So it is equal to Va max. Va max is equal to zero point 0.9 Vs. As alpha is increased, average output voltage decreases till at alpha equal to 90 degrees, cos 90 is 0 and average output voltage becomes 0. So this is 0 degree, this is 90 degrees, this is 180 degrees. And here it will come down like this. At alpha equal to 0, average output voltage or armature voltage is Va max, it's 0.9 Vs. As alpha is increased, average output voltage decreases till at alpha equal to 90 degree, average output voltage becomes 0. When alpha is made greater than 90 degrees, average output voltage becomes negative. So it goes negative till at alpha equal to 180 degrees. Cos 180 is minus 1, average output voltage is maximum negative. That is minus 2 root 2 Vs by pi or minus 0 0.9 Vs. So this is minus Va max equal to minus 0.9 Vs here. This will happen at alpha equal to 180 degrees. Okay, so that means यहाँ से यहाँ तक your converter is operating from 0 to 90 degrees, it is operating in the rectification mode. And from 9 to 180 degrees, it's operating in the inversion mode. In the rectification mode, your converter is taking electrical energy from the source and supplying that electric energy to the motor. Motor is operating in the forward motoring mode, converting electrical energy into mechanical energy, which is used to drive the load. From 90 to 180 degrees, our converter is operating as a line commutated inverter, not as a rectifier. It is operating in the inversion mode because average output voltage becomes negative. So in this case, our machine is not operating in motoring mode now. It's operating in the regeneration mode. It is converting mechanical energy into electrical energy, and that electrical energy is given back to the source through this inverter. So inverter takes DC energy, converts that DC into AC and supplies that AC back to the source. So this is VA, average output voltage versus alpha, delay angle. Okay, so this is about full converter. What about half converter or semi converter? I will write here semi converter. It may be single phase semi converter or three phase semi converter. A semi converter is symbolically shown like this. First of all, let me draw a complete power circuit diagram of a semi converter. It comprises of two thyristors and two power diodes. This is the AC source, maybe through transformer or it may be without transformer, and this is your load. Load is DC motor like this. This is back EMF, this is armature circuit resistance, armature inductance, and this is separately excited field. Field current is IF. And symbolically, this semi converter is shown like this. Symbolically, we show the semi converter like this. Thyristor in series with diode, because in each leg you can see thyristor diode. So it is single phase supply, so it is AC. यह आपका load है, which is a DC motor. This is back EMF EB, this is RA, this is LA, this is average output voltage or armature voltage VA, this is current IA, and this is the field current IF. For a semi-converter, the average output voltage is given by a different equation, that is given by root 2 Vs by pi times 1 plus cos alpha. I am sure that you know about this. For alpha equal to 0 degrees, cos 0 is 1, 1 plus 1 is 2. So average output voltage is maximum, and that is equal to 2 root 2 Vs by pi, just like a full converter, and it is equal to 0.9 Vs, and it is equal to Va max. So for alpha equal to 0, Va is equal to Va max, and that should be equal to the rated voltage of the motor. Okay. Then as you increase alpha, average output voltage decreases till at alpha equal to 180 degrees. Cos alpha is minus 1. Minus 1 plus 1 becomes 0, and average output voltage becomes 0. I will write here, as alpha increases, average output voltage decreases till at alpha equal to 180 degrees, average output voltage becomes 0 because cos 180 is minus 1 plus 1 becomes 0, so average output voltage becomes 0. So therefore, our in the quadrant operation, you will see that if this is the positive current, this is the negative current, armature current, this is the positive voltage, this is the negative voltage, it will operate only in first quadrant. It will not operate in fourth quadrant. Your phase control full converter was operating in the first quadrant and fourth quadrant. It was from 0 to 90 degrees, it was operating in the motoring mode, that's first quadrant, and for 90 to 180 degrees was operating in fourth quadrant, that is as inverter, regeneration mode. So your converter for 0 to 90 degree, that means full converter, was operating as a rectifier in first quadrant, and from 90 to 180 degrees it was operating as an inverter in fourth quadrant. But semi-converter always operates in the rectification mode. It cannot operate in the inversion mode. Why? Because average output voltage never becomes negative. It always remains positive. Okay, so therefore, if this is the DC motor, we can operate this DC machine only in the motoring mode. It's not possible to operate it in the regeneration mode. Why? Because the converter does not have capability of operating as an inverter. It always operates as a rectifier in only first quadrant. It can operate only in forward motoring mode, not in regeneration mode. So therefore, in those applications where you do not require braking or regeneration, semi-converter can be used, because semi-converter will have some advantages, like instead of using 4 thyristors, it's using only 2 thyristors, so cost is less. And secondly, it gives better input power factor. That I'm sure you know that a semi-converter gives better input power factor than a full converter. It is less costly and it gives better input power factor. But in those applications where braking or regeneration is also required, you cannot use semi-converter. You have to use a fully controlled converter there, or full converter. So I will again write average output voltage VA is equal to root 2 Vs by pi into 1 plus cos alpha. You can plot it like this. This is alpha versus average output voltage VA. For alpha equal to 0, average output voltage is maximum, that is VA max equal to 0.9 Vs, because 1 plus 1 is 2, it is 2 root 2 Vs by pi, that is 0.9 Vs. As alpha increases, average output voltage decreases. This is alpha 90 degrees, this is alpha 180 degrees. At alpha equal to 90 degrees, cos alpha is 0. So it is root 2 Vs by pi. Okay, average output voltage is half of this, that is 0.45 Vs. Root 2 Vs by pi means 0.45 Vs. So average output voltage half हो जाती है. So it is this much. Then as you go towards 180 degrees, average output voltage falls till at alpha equal to 180 degrees, average output voltage becomes 0. So you can see with alpha, this is the variation of average output voltage or average armature voltage. So your converter operates only in rectification mode. It does not operate in inversion mode. Therefore, in those applications where inversion mode of operation is also required, semi-converter fed DC motor drive cannot be used. You have to use full converter fed DC motor drive. So I will stop here. So this was a general overview of a DC motor drive, how a DC motor drive can be supplied by I started with simple half wave converter. For low voltage, low power ratings, you can use a half wave converter. And for ratings up to 10 kilowatts, you can use single phase converter fed drives. And for greater than 10 kilowatts, up to thousands of kilowatts, you have to use 3-phase converter fed drives. Okay, 10 kilowatt tak single phase converter fed drives. Now single phase converters are of two types, semi converter and full converter. Full converter operates in first and fourth quadrant. That means for a range of delay angle from 0 to 90 degrees, it operates in the rectification mode, and your drive operates in the motoring mode. And for range of delay angle from 90 to 180 degrees, it operates in fourth quadrant, that is in inversion mode, and your drive operates in regeneration mode. It may be forward regeneration mode or reverse regeneration mode. We have taken both the examples. Whereas on the other hand, a semi-converter operates only in first quadrant, that is as a rectifier in rectification mode only. Therefore, the DC motor drive fed from semiconverter, whether it is a single phase semiconverter or three-phase semiconverter, does not have capability of regeneration. It operates only in forward motoring mode, not in regeneration mode. So with this background, we will have more analysis of converter fed DC motor drives in next class. Thank you.